What if your data set for regression or for neural network prediction has so much data that it just takes way too long to evaluate the entire objective function and especially get the gradient for the entire objective function? Maybe you could take a statistics frame of mind and say, well, instead of working on the entire data set, let me just take a random sample of it. In the same way that we might say, if I want to know what the prevalence of a genetic condition or something like celiac disease is in the entire US, I don't need to sample all 300 million people. I could just sample like a few thousand and get a confidence interval around the proportion I get from that. We won't be doing confidence intervals, but the same basic idea applies that even when you have a huge population, a reasonably sized sample can still give you really good information about the whole population. So what we're going to say is take a sample from your entire data set, run a step of gradient descent on that, and then for your next step, take another sample, run gradient descent on that one. So rather than just taking a sample and running that all the way to completion, multiple gradient steps and stuff, we'll take a new sample every time from our data set. When you've taken enough samples that you've hit every data point in the data set, I know that's not what we would actually do if we were sampling the US population, but it's common in what we're doing here. Once you've seen every data point in your data set, that's called an epoch, E-P-O-C-H, and then you might run multiple epochs. So this idea is called stochastic gradient descent. The stochastic means random. We're taking random samples. Our derivative vectors or gradients are going to be pointing in slightly random ways as we move around. And the question is, how much randomness? This relates to the big trade-off. Do we want to take really good steps that take a long time, or do we want to take not so good steps, but the steps themselves go faster? And there's just always that trade-off. So let's look through here. So we're going to set up some data for linear regression. In our previous notebooks, we just used data that was on a perfect straight line because that made the mean squared error 0 at optimality. But that isn't very exciting when we want to talk about stochastic regression and real data sets. So we're going to set up data with some noise in it. And notice here I'm going to be setting a random seed so I can reproduce exactly the same noise if I want to run this whole thing again. That's an essential part of doing reproducible machine learning or other data science or even statistics research. So I'm choosing a seed. Our class is math560, so might as well choose 560. It doesn't really matter exactly what you choose. I could just say np random seed 560, but this way I can refer to the seed I set later. I could put it in a title legend, or I could put it in a data set that I'm saving to disk. So it's good practice to do it this way. I'm setting up, here's my the underlying intercept and slope for my linear model. I'm setting up a bunch of x values starting at 2, stopping at 8 by steps of 0.01. And then the exact values, and then adding some random error. So here's the data set we get. This is 600 data points. It's a nice number. So let's go see what happens. First, let's look at the contours of the objective function. Have they changed much from when we had an exactly perfect straight line data set? They look pretty much the same. So we're still working in the same basic problem. We're still going to be starting at 0, 0 and hoping to find our way to the minimum here. We're going to run plain gradient descent on the data set so we have something to compare with the stochastic gradient descent. One thing we have to remember is before the best possible mean squared error was 0 because our data fell exactly on a straight line. Now it's not going to be 0 anymore, so we're going to check what that actually is. So I'll use a learn rate of 0.03, which worked well before. And thinking about learning rate decay, I'm going to start with no decay. And then later we'll come back and see what having some decay does. If I have two things in a row like this, which one wins? It's whatever happens last. So this sets learn rate power to 0.5, and then this comes along and sticks 0.0 in there. So the 0.5 is gone in memory by the time you get here. So sometimes it's nice to leave kind of a record of things you've tried or a few options, and you can always grab one and copy it and paste it down here to make it the one that's active. So let's take a look at what just the plain steepest descent does here. The red plus sign is at 1,000 epochs. So remember, one step of gradient descent is an entire epoch, non-stochastic gradient descent. So in 1,000 steps, it gets from our starting point to basically the optimal solution. This is with no learning rate decay. So in the next video, we'll actually try stochastic gradient descent and see what happens.